But in this method, there are certain limitations of that. Main limitation, it is too subjective actually, and it is location and time specific is a problem. Then we have statistical method. In the statistical method, actually regression equations are being set up between predictor and predictors, and then by testing the correlation coefficient, the regression equations are set up, and these regression equations are these are again used for the prediction. While setting up the regression equation, we used to use the historical data set. Using the historical data set, the regression equations are set up. Again, historical data set is again divided into test data and training data, etc. And in India, our summer monsoon rainfall long-range forecast used to be done by this statistical method since for a long time. But in this method also there are some problems. And the first problem is that this correlation between predictor and predictor, they changes time to time, place to place. Even for a given place and time, correlation changes. And another one thing, in statistical method is a problem. They are very good in predicting the mean, that is normal. But there are problems when some extremes are there. Then come your present days, which we used to do, that is called numerical weather prediction. In the numerical weather prediction, there is a first basic realization, which I already told, that weather at any place at any time, it is a function of several basic parameters, which is given like this: weather as a function, weather at a spatial point x and t is a function of this u, v, w, p, and all of them are function of x and t. So therefore, if we know these variables for the future value, then it is possible. So therefore, we can see that forecasting weather has been translated into the forecasting of these variables. But for that, actually, what do we know? What do we require? We require a governing equation, that is rules. And fortunately, we have the governing equation. We have governing equation, that is momentum equation, continuity of mass, continuity of moisture, and your thermodynamic energy equation. They provide us the physical laws for the time evolution of momentum, time evolution of mass, time evolution of humidity, and the time evolution of temperature, and it is close by your equation of state, that is P is equal to rho RT. And for the initial condition, we have a very robust observational system, and those robust observational system, this provides us the initial condition. Now, NWP has a history. It was first 1904, Bill Bartlett realized that it's a problem of initial value problem. Afterwards, in 1922, Richardson attempted, but he failed. And afterwards, after the invent of the electronic computer, actually in 1950s, a group of three scientists, they developed the first operational weather prediction program, and it was successful. Afterwards, NWP never need to look back. This is a broad structure of an NWP. This is your geophysical environment, you can see, and observations are taken, globally measured data set, then data collections are there and they are processed, then there is some data assimilation is there, and after that assimilated data, it goes to mathematical model, and then model output goes here, statistical interpretations are also afterwards. This weather prediction. As I told you, this is a graphical picture of the global observing system. You can see the different components of the global observing system. Upper aircraft is there. Then for your ocean data, buoy is there. Satellite is there. Different types of satellites are there. Okay. Then your aircraft observation. Then your man-made observations are also there, automatic weather stations are also there, radar is also there, and many observations. These are the basic components. Then whatever observations are being taken, those observations are not advised to directly send to the mathematical model, even if you cannot send also. Because whatever observations we are taking, those observations are being taken at unevenly spaced point, and unevenly spaced observation you cannot fit to a So therefore, what it is required, it requires to be converted to a evenly spaced data, and not only that, it needs to be clean. So therefore, it requires some pre-processing, which involves your quality control, then temporal consistency, spatial consistency, and as I told you, converting the observed data to model data. Model data means readed data, and we need to remove the errors or imbalance from the readed data also. So then in the pre-processing, as I told you, one method is called objective analysis, where just readed data are prepared from the observed data, and another one is called initialization, where from the readed data, disturbance or imbalance are removed. Okay? Then once it is, and nowadays, entire thing is being done by a system. This is called data assimilation. You can see O stands for observation. This observation, it goes to DA. DA means data assimilation system. Then this is the data cache. In the data cache, many things are there. Error statistics are also being prepared. This data is there. Model data is there. Observation is there. Model means a forecast model actually. A forecast model which gives you a short-term forecast, only 6-hourly forecast. That only. And what it is being done here actually, where actually this balance is being done. There this is pictures. Observation comes, forecast comes. It is compared. After comparing, two things are done. Either you have to reject or you have to adjust. Okay? And then it goes to numerical model, and from there forecast comes. And from one part of the forecast, it goes as one input in the data assimilation system.
There is a sorry, can I ask a question?
Yeah.
What is that? There is a latency between forecast and observation.
What is that?
There is a time difference.
6 forecast and
Observations.
yes, sir. I am telling actually observations are taken at some synoptic hours of observation. Synoptic hours of observation, this is globally fixed. Every 3 hours, 0 GMT, 3 GMT, 6 GMT, like that actually. And this model, what I am telling you, sir, this say one numerical weather prediction model, it is being run and 6-hourly forecast only. 6 hours, which is valid for say. For example, now it is say 4:30. So that means we have to use one forecast data which is valid at 4:30. That means at 4:30 I am having the observation also, I am having the model also. And now question is, definitely we may ask, sir, that why model is that? Because model data, it is that data which satisfies those equations. That means it is a balanced data. And observed data is a real data. Okay, so that's why this model and observation both are compared.
My point was that suppose you say that forecast was done for next 3 years. So if you cannot compare, say now it is 4 o'clock, you forecast for 7 o'clock. Okay. And when you go,
Yeah, let me tell you, sir. Actually, there is a cycle is there. We call it data assimilation cycle. That these cycles, there are some cycles that one is 0 GMT, one cycle is there. In this 0 GMT cycle, it takes a window. Here it is 3 hours before, 3 hours later. Okay? Then within this period, whatever observation, whatever model data comes, that will come to this cycle and this process will be done. Then it comes together. Thank you. So this is the thing, data assimilation system. And actually this data assimilation is being done by a very sophisticated mathematical way that is called variational data assimilation. That is variational technique we are using actually. So where actually what happens, one cost function is defined and that cost function is minimized. And that for which value of the variable that cost function is minimum, that is your initial function, balanced initial function. That only can go to the model. This slide will be here, so in details you can see. And this is the model equation as I was telling. These are all tendency equations. 3 components of the wind: temperature, density, relative humidity, specific humidity. And to make the system closed, equation of state is there. All equations are tendency equation. And another one thing, definitely this equation has to be written in a spherical coordinate because our earth is spherical. So, and by solving this equation, what we will do, we will get the future value of this variable. But definitely we know, and solving is done. Now, while solving, there are certain issues out there. Issue is, first of all, this equation cannot be solved analytically. This is number one, because these are non-linear partial differential equation. Non-linear partial differential equation cannot be solved analytically. Another one reason is these coefficients of the differential equation, we don't know their analytical form. So as a result of which we are bound to solve it using numerical method. So there are two methods are there. One is your numerical methods, another one is spectral method. Numerical method, this is the basic, that is every derivative is expressed in terms of some finite difference, and by knowing the present one and the known function, we can find out the future value. And besides, there are another one method is also there, that is called spectral method. Spectral method, the main purpose of the spectral method is that at least the x variation and y variation we can have some analytical expression. So for that, every variable, we know that every variable is a function of x, y, z. X and y variation, it is expressed in terms of waves, Legendre and Fourier. For x variation, Fourier; for y variation, Legendre. Okay? So in the spectral method, as a result of which, at a given level, we are able to evaluate exactly this one. So that at a given level, all this equation, partial differential equation, converted into ordinary differential. And then ordinary differential equation solution we know. Okay. But in this method also there are a lot of issues are there. One is called aliasing effect is there. Aliasing leads to your non-linear instability. Issues are there. So later on, actually now it is in the nascent state that in the spectral method we see we are using what? We are using your global orthogonal function. Whatever we are using, these are nothing but a global orthogonal function. So now nowadays actually what happened, another one method has come, that is your finite volume method, finite element method. They are actually orthogonal function we are using, but they are local orthogonal function. Let me suppose entire line I divide it, x1, x2, x3, x4 like this. I define one function which is orthogonal between xi and xi plus 1. For xi plus 1 and xi plus 2, there will be another one orthogonal function. So like that actually some problems are really, but still it is going on. And now question is, after getting this future value of this one, what is the use of that? It is of no use unless it is being post-processed. So that's why it is being post-processed. So in the post-processing, what we do model output statistics, we do downscaling. Downscaling means suppose you have generated the forecast for this entire row, but you want a forecast at your place, this one. So therefore, whatever forecast product you are getting, that needs to be downscaled. So that is also being done. And then another one thing is that suppose whatever weather being forecast, whether it is having any impact and associated risk, that is also being assessed. As I told you, downscaling it is nothing but generation of NWP products at a relatively finer resolution. And there are two methods of downscaling are there. One is your statistical downscaling, another one is your dynamic downscaling. Statistical downscaling is very simple thing, that is regressive equation setting up. Dynamical downscaling means within a model another one. One model is there with some Poisson resolution. Let us say one model is there with resolution 50 km. Within that, I am next another one model I am putting that is having the resolution say 20 km like that.
When you say downscaling, it is only tertiary or downstream. Can it be done in the temporal scale also?
You don't require the sir, because suppose one forecast is generated, which is valid at 5:30 hour, 5:30 p.m. Now 5:30 p.m. and that forecast has been generated for this room. Now you require what will be the forecast valid at 5:30 p.m. in a smaller region, na? That's all. That's right. Now question is that still we the general people.
What is the strategy to address that missing data? For example, you say that input data.
Yes. And first strategy is your that is your first of all we have seen that there are different observing systems. One observing is a man-made one. We will both take the observation. But for that we require an observatory everywhere. We cannot have the observation. For it is substantially automatic weather station. For example, জঙ্গলে যদি আপনার দরকার হবে জঙ্গলে তো আমরা গিয়ে করতে পারছি না অটোমেটিক ওয়েদার স্টেশন দেন satellite observations. So in this way and still I cannot say that even if we take all the observational component it covers them. No, still there are certain data gap vision is there that is being filled up here by objective analysis, what I told you. Objective analysis, suppose I am having an observatory here, but I want input here. I will use some sophisticated interpolation. But while doing the interpolation, I already inserted some error. And that error in terms of physics we will call it is an imbalance. And as the model runs, imbalance will also grow. And in time, entire forecast region will be occupied by this imbalance. So therefore, শুরুতে এদেরকে শেষ করতে হবে. That means at the initial time itself, this imbalance needs to be checked. But we cannot say it is 100%, but within a tolerance limit. Always we do within a tolerance limit. So that is initialization. But nowadays now, initialization, objective analysis, all are being done together in a system which I told you, data assimilation. 4-dimensional, variational data assimilation.
And validity also one kind of instrument which can gather the information.
Pardon, sir?
And validity.
Radar, yes, radar. I have shown. I think I can show you that picture again. Radar, of course. Radar is very yes, and radar is there. Radar is there.
Yeah, middle. Yeah.
Radar is a different band radars are there. Radars are there.
Means one of the observation can I ask
Yes.
that you see this is a very primitive radar kind of thing, right? It is only one dish and like
Then that is the
like
just
the
one.
radar we have in our city.
Correct.
There is a base array.
Yes.
And now the question which you have raised,
Yeah.
spatial and temporal,
Correct.
that errors
Yeah.
that can be accommodated using this
Exactly
base
so.
band.
Exactly
So
so.
I can change the beam weight
Tick.
so that I can more pinpoint the resolution.
Exactly, we do, sir.
Huh?
We do also like that. From one source of observation, when we are confirmed that there is something, then immediately.
Then you change.
Another some more thing I should have created, that is wind profiler. Wind profiler is also very much useful. Wind profiler. And then another thing, the radio. We know now radio occultation. Radio occultation is also very useful information. That is when from the radar being when it enters into the atmosphere due to refraction it bends, no? And while bending, depending on the atmospheric composition, its bending will be there. Accordingly, those data will be retrieved. So observational system is very important. Meteorology is an observational science. Whatever mathematics we do, unless we do the observation as told in covering the ideal situation is covering the entire globe. That should be the main thing actually. So that's why Government of India through India Meteorological Department this time they have given a new project that is called Mission Monsoon. So one of the component of the Mission Monsoon is observational network expansion. That's why, sir, you remember, we are showing interest to enter into the MOU with different institutions. One of the purpose is that institution will allow us some space to put some automatic weather stations so that we will get the observation. Because observation has to be increased, otherwise we cannot. Okay, so yeah, that is over. Still, you know, still we know very well that our forecast is not one. It is not our means. I am not going to say in India or what the word is. We know that there are imperfection in the input and the model also. So our input is imperfect. The model is also not perfect. Why I am telling? Because if you remember, if you see this equation, right hand side everything is nothing but the forcing for changing the left hand side variable. We have written only those forcing which we know and which we know how to represent mathematically. We are not able to put any other forcing, maybe important forcing which we don't know, and at the same time we feel that forcing is there, but we are unable to express them explicitly in mathematical terms. So that means even this mu, this is also not same everywhere. We don't know an uniform value of mu. So that means these equations are not perfect. Another one imperfection is that if we look this equation, this is actually a variant of the first law of thermodynamics. And that first law of thermodynamics only we have used, which is the variant of the reversible thermodynamic process. But we know very well, in the atmosphere, whatever thermodynamic processes are taking place, then we cannot say this is 100% reversible thermodynamic process. There may be, and there are irreversibility in the different thermodynamic process. So that we are not able to incorporate. So as a result of which, our model is not perfect, our equation is not perfect. So that as a result of which, what happened? Definitely there are certain amount of uncertainty there in the forecasting. So now question is, next stage our scientists started making an attempt how to address, to quantify this uncertainty. For that actually, this is the reason of what I told, and this actually we all know that in 1963 Lorentz discovered the fact that atmosphere, like any other dynamical system with instabilities, has a finite limit of predictability. Because our models are non-linear, our systems are non-linear systems. Okay? So now what to do to address this uncertainty? Then it comes the ensemble prediction system. Ensemble prediction system is not, this is nothing but an NWP system. But thing is, here actually we don't generate a single forecast for a given weather phenomena. We try to generate many number of forecasts for a given weather phenomena. Now question is, for that, what we can do? We have two options. One option is that we should have many models, and each model will use the same initial condition, they will produce the forecast. This is one way. And if I don't have the many models, what we can do? We have to pattern the initial condition to generate many initial conditions, and using each initial condition we have to generate the forecast. As a result of which we will have a good sample of forecast. Now once we have a good sample of forecast, we can do a lot of statistics. We can find out the variance, and magnitude of the variance will tell us how much reliability is there in the forecast. Then question is, we can have lot of probability If I say 70%, so quite natural the user will take it with a little relatively more confidence. So this was the ensemble prediction system. As I was telling, actually, this is the in picture it is shown. And ensemble may be good also, ensemble may be bad also. This is this is an example of the good ensemble where the truth one, ensemble average and other thing they are with the towards the truth, and this is the bad ensemble. Okay. And these are the different products as I told you. And now since I am from the meteorological department, I am tempted to tell what is the forecasting system in my department. India Meteorological Department, we are having a seamless weather and climate forecasting system. We are having forecasting system which is valid up to 6 hours for all types of severe weather, that is thunderstorm, turbo, all these things. So many at all districts and so many stations. Then we are having short to medium range forecast for rainfall over cities, blocks. Then we are having extended rainfall. This is very useful actually by the administrator and other stakeholder. That is 4 weeks forecast we give, and it is being issued every Thursday. And what are the things we forecast? Average picture of the wind, rainfall, maximum and minimum temperature, and another one is your seasonal. And this is the integrated approach. You can see these are different observations. All observation goes to regional telecom hub, and here actually all these data assimilation takes us, then it goes to different places, and after forecast it goes to general public and your what is called general public stakeholders. Government is also stakeholder. Now nowadays in forecasting means NWP. Now in the NWP, what are the progress and what are the opportunities we can see? Progress of the NWP, as we have seen, it is driven mainly by the advanced data assimilation, improved representation of the physical processes, because there are many physical processes that are taking place. One is your convection, that is cumulus cloud and all this is small scale. Then your radiative processes, then boundary layer, all these things, and ensemble forecast. These are then ensemble forecasting allows for the integration of multiple simulation to assess the forecast uncertainties. And this method enhances the reliability of the forecast, particularly for extreme weather events. Then now we are going for kilometer scale model, because we have understood that that is convection, cloud microphysics, all those things. Even if we are trying our level best to parameterize, but it is not getting perfect. Sometimes it is giving us very good results, sometimes they are making us failure like anything. So that's why the World Scientific Community, now they have decided they will go to global kilometer scale model. That means resolution will be 1 to 3 kilometer like that, global. So that we can imagine how many grid points will be there, how much data is required, and how much computing capability there is there. So of course our ambition is very high, but this is a definitely very challenging thing actually. And development of high resolution global models running at scales close to 1 kilometer is one of the latest advancement in NWP. And these models promise to reduce the need for parameterization will not require that. And this resolution requires, of course, significant computational power, and this poses a considerable challenge to the complex process. So now these are the challenges and future evolution of the NWP model. I am finished, almost finished.
I have a small
Yes.
that what is the need for having predictions every 1 to 3 kilometers?
Yes.
I mean,
Yes.
can change.
Yes, right. Actually, I am telling you, 1 to 3 kilometers you don't go that. Well, let us consider sub-grid scale. For every numerical model, there is a grid scale. For example, right now in one global model is there, which is the most high resolution, that is 12 kilometers. 12 kilometers by 12 kilometers, 10 to 12 kilometers. But some 10 to 12 kilometers is this one. Now within this 10 to 12 kilometers, there may be a cumulus cloud convection. with it. So that cumulus cloud development and everything, this will be mixed. This will be mixed. Why this big?
Is that your average?
Yes,
It was not discussing this.
Then now, then there
My
will be
grades
an average.
subject
What is that?
Average.
has not been
No,
discussed.
sir, actually it will be.
Why you need 1 kilometer?
This I am coming, sir. This I am coming.
My
First of all,
concern
before that we should know why we need parameterization. Then automatically it will be. So this is the grid. In this, so if I am having some weather which is covering at least one grid, I will be able to capture. But suppose something is happening in there, then no one is seeing this chore. Okay? Now what happened during its development, something will be done. For example, strong downdraft. And this strong downdraft will definitely influence the temperature and humidity at this grid point. That means at this grid point, any special weather has not been given, but suddenly there is a change. So therefore, if I fail to take the effect of this phenomena, subgrid scale phenomena, then systematically, knowingly, we will be missing some information. So this was the reason behind parameterization of subgrid scale phenomena. For that, lot of schemes are there. But what happened, as I was telling, those schemes actually sometimes they are producing very good results. So that's why now people are thinking, why not we should have a grid which will cut it, 1 kilometer scale. Because their scale we know, that is, this is your of the order of 10 kilometers. This is the reason. Have I been able to clarify your
Yeah,
doubt?
I mean, yes, somehow I can visualize that, but at the same time, I think this is more applicable to, like places where they have tornadoes, like in the US.
Yes.
Because that usually
Correct,
occurs within a few
Even for thunderstorms,
tens of meters.
even thunderstorm also. Thunderstorm many times it is being missed due to this one. So that's why this has been failed. This has been failed. Why scientist community? So no, parameterization কিছু হবে না, অনেক হয়েছে, অনেক পয়সা খরচা হয়েছে। তার থেকে একটা কাজ করা যাক, one step, that is your kilometer scale model. কিলোমিটার স্কেলে ধরুন আমার উপর দিয়ে ধরুন এত বড় একটা করছে না, আমি বেরিয়ে চলে গেলাম দিয়ে এবারে এমনভাবে ইম্প্রুভমেন্ট হতে যাতে করে আমার উপর দিয়ে যায়, তা আমার পাবেন না, এখানে বুক, এখানে অমুক পশু ইত্যাদি পাবেন ওই রকম। আমি মানে কিউলাস ক্লাবটা দেখে
Most of the weather we see very localized.
হ্যাঁ, দ্যাট ইজ অলসো। স্যার লোকালাইজ করতে গেলে আপনাকে লোকালাইজ করতে চাই, লোকালাইজ করতে চাই আমরা। হ্যাঁ, ওটা তো প্রয়োজন স্যার, কিন্তু কথা চলবে না। এটা হচ্ছে সেই বাড়িতে ছেলেমেয়ের মতো, আমি এটা করতে চাই, কিন্তু বাপের যদি পয়সা না থাকে তাহলে এটা হচ্ছে এইরকম আর কি ব্যাপারটা, যেটা তো করতে চাই। দুনিয়া তো বলে দিল, কোথায় গেল দুনিয়া বলে দিল এটা চাই, কিন্তু কথা তুমি তো সায়েন্টিস্ট, উনি বলে দেবেন, কিন্তু পয়সাটা দিতে হবে গভর্নমেন্টকে, ঠিক আছে না? এবার গভর্নমেন্ট যখনই পয়সা দেয় না, গভর্নমেন্ট একটা জিনিস দেখে, যেটা করছো তাতে আমরা যেটা লস করছি সেটার জন্য কত আমার, আর যেটার জন্য তুমি এক্সট্রা পয়সা চাইছো তাতে কতটুকু বাঁচছে। Government in that case, any government, I am not a political person, every government is having a typical banana attitude actually, and it should be so, after all taxpayers' money, they cannot play it. So, that's why actually this is required. Another major challenge is the computational demand for the high resolution. For running global model simulation, after consult at kilometer result requires immense computational.
বলতে যাচ্ছি
হ্যাঁ, অবশ্যই।
সবাই যদি এত পাওয়ার যায়, এত লোকালাইজেশন যায়, তাহলে ওটা কে দিবে? গ্লোবাল ওয়ার্মিং কি হবে?
একদম। ওই জন্য স্যার পরের ব্যাপারটা, এর পরের কথা আমি আসছি, আমাদের স্টুডেন্টদেরকে উদ্বুদ্ধ করা অবশ্যই, একদমই। তারপরে ব্যাপারটা হচ্ছে কি, যে ব্যাপারটা হচ্ছে already we know that during our data assimilation we are integrating many complex data. মানে আমি চিন্তা একটা সিম্পল এক্সাম্পল দিচ্ছি, আপনারা যে দেখলেন ইনপুটগুলো, ওই ইনপুটের মধ্যে কিন্তু কোথাও আমার না রেডিয়েটিভ এনার্জি ফ্লাক্স ছিল না, ইফ আই কারেক্টলি রিমেম্বার, আপনারাও দেখেছেন কোথাও ছিল না। এবারে স্যাটেলাইট থেকে ইমিডিয়েট ইনফরমেশনটা কি চাই, কি যোগদান, ইজ নাথিং বাট এনার্জি অনলি। করছি কাকে করছি, টেম্পারেচারে করছি। E is equal to sigma T to the power 4 ওইটা করে টেম্পারেচারে করছি। এরকম আরো অনেক আছে, এটাতে জাস্ট আমি একটা एग्जांपल দিলাম। এরপরে কি হয়েছে বলুন তো দেখি, যখন একটু আগে স্যার প্রশ্ন করলেন এই সাইকেল আমাদের কোনো একটা জিরো সাইকেল হয়ে গেল, নেক্সট সাইকেলে আবার আপনাকে ওই সব ডেটাগুলো দিতে হবে। মানে আগের সাইকেলে যদি আপনি স্যাটেলাইট ডেটা দিয়ে থেকে থাকেন, এই সাইকেলে আপনাকে দিতেই হবে। এবারে বড় কোনো ওই সময় আপনার স্যাটেলাইট ডেটা নেই, স্যাটেলাইট পাস করছে না, তাহলে কি করতে হবে, ওই যে ফোরকাস্টে আপনি টেম্পারেচারটা বার করেছেন ওটা থেকে আবার কনভার্ট করতে হবে এনার্জি। তাহলে আমরা বুঝতে পারছি কিরকম কমপ্লেক্সিটি আছে। এবারে এই কমপ্লেক্সিটিটা কি হারে বেড়ে যাবে বুঝতে পারছেন যখন আমরা কিলোমিটার স্কেলে করব। সুতরাং দিস আর দ্য চ্যালেঞ্জেস। ইপিএস ও অনেক চ্যালেঞ্জ আছে, এই জন্য এখানে আসছে আমাদের আর্টিফিশিয়াল ইন্টেলিজেন্স, মেশিন লার্নিং, ন্যাচারাল ফাঁকা মাঠ যেভাবে সিক্স সেখানে গোল করার চেষ্টা করবো। তো এখন ওখানে অনেক প্রবলেম, এই জন্য আপনার কথা হচ্ছে why AI and ML in weather forecasting required. As I told, the physics-based forecast model computes future values of basic meteorological parameters, then post-processing this. These computation require large computing. আমরা অলরেডি ডিসকাস করলাম, আমরা সকলেই জানি, আমিও ML অতটা জানি না, বাচ্চারা সবাই জানে হয়তো। ML uses a lot of data to produce result, and প্রত্যেক ওয়েদার ডিপার্টমেন্টে কিন্তু প্রচুর ওয়েদার ডেটা আছে, ফোরকাস্ট ডেটা এবং সব রকমের অবজারভেশন ডেটা, মানে ডেটা প্রচুর আছে, ঠিক আছে। এবারে ML কি করতে পারে, ক্যান এনহ্যান্স দিস কম্পিউটেশন বাই অ্যাডিং কম্পোনেন্টস অর রিপ্লেসিং সাম পার্টস অফ দ্য প্রসেস ভায়া অ্যান হাইব্রিড অ্যাপ্রোচ। Instead, ML can also fully replace the whole model at a much lower computing cost. Already report আছে এরকম যে আজকের দিনে হাই রেজলিউশন এনসেম্বল সিস্টেমের মডেলের থেকেও অনেক আগে কিন্তু এবং অনেক কম খরচাতে ওরা অনেক সঠিক আউটপুট দিয়ে দিতে পারছে। কিন্তু একটা আউটপুট থেকে তো আমরা ওটাকে জেনারেলাইজ করতে পারি না, হ্যাঁ, বাট অ্যাট দ্য সেম টাইম ওটাকে ইগনোর করাটা ঠিক নয়। নতুন যখন এসে ওদেরকে এমব্রেসও করে নিতে হবে। In addition, AI/ML opens some avenues in other activities such as extreme weather prediction, such as flood forecast, fire danger forecast, যেগুলো আমাদের দরকার, monitoring of observations, managing the supercomputer, or enhancing user experience, etc. These are different potential applications of AI/ML. The use of AI trained on existing parameterization, but replacing the existing parameterization
यहाँ पे पढ़ा है ना
can reduce the computation of cost of the parameter. Existing parameterization মানে যেগুলো existing parameterization করে যে রেজাল্টগুলো আমরা পেয়েছি ওই রেজাল্টগুলোকে ট্রেনিং ডেটা হিসেবে ইউজ করে একটা ওরা প্যারামিটারাইজেশন দিয়ে বার করতে পারে, আর সেটা কি করতে পারে, সেটাকে এক্সিস্টিং প্যারামিটার স্কিমটাকে রিপ্লেস করে দিলে তাতে কি হয়েছে, রেজাল্টটা অনেক অ্যাকিউরেট আসার পোটেনশিয়াল আছে এবং খুব তাড়াতাড়ি হওয়ার সম্ভাবনা আছে। Instead of running small limited area model ensembles, many scientists এটার জন্য আপনার অ্যাডভোকেট করে, sophisticated AI schemes may be applied to directly calibrate and downscale the output. এগুলো কিছু স্টাডি আপনাকে আমি উল্লেখ করে রাখুন, there are many studies actually. এই একটা স্টাডি, রিসেন্ট স্টাডি, ওরা একটা লাইটনিং এর ক্ষেত্রে দেখেছে যে AI enhanced algorithm আপনার ECMW আজকের দিনে সবথেকে সেরা মানে মডেলিং সিস্টেম, ওদের যে হাই রেজলিউশন মডেল আছে তার থেকেও ভালো ফোরকাস্ট দিচ্ছে এবং তাড়াতাড়ি দিচ্ছে, মানে পোটেনশিয়াল, এটা একটা কেস। এই যে মেশিন লার্নিং অ্যাপ, এটা করে এগুলো হচ্ছে আমাদের এন্টারপ্রাইজ ডিফারেন্স কে মেশিন লার্নিং কিন্তু প্রত্যেকটাতে হেল্প করতে পারে, প্রত্যেকটা কম্পোনেন্ট এটা হেল্প করতে পারে। এটা হচ্ছে ক্লাইমেট আর্ট সিস্টেম, ইট ইজ অ্যান ইন্টিগ্রেটেড সিস্টেম, গ্রাফিক্যালি দেখানো হয়েছে। এআই অ্যালগরিদম ইন্টিগ্রেশন, এরা ক্লাইমেট ডেটা এবং আদার ডেটাকে ইন্টিগ্রেশন করতে পারে, টাইম সিরিজ অ্যানালিসিস, স্ট্যাটিস্টিক্যাল এস্টিমেশন, প্যাটার্ন রেকগনিশনটা খুব ইম্পর্টেন্ট, দেন ক্লাইমেট মডেল ডায়াগনোস্টিক, এই সমস্ত জিনিসগুলো এগুলো করতে পারে, এগুলো বিভিন্ন লেয়ার। এবারে কথা হচ্ছে যে আমাদের আবার ওভার এনথুজিয়াস্টিক মানে ওভার এক্সপেক্ট করাটা উচিত না। এই পিকচারে দেওয়া হয়েছে এটা কতটা করতে পারে, আর কি দেখুন এখান থেকে এটা হচ্ছে স্কেল, মানে দুটো একটা সিম্পল পোস্ট প্রসেসিংটা খুব সুন্দরভাবে এরা করতে পারবে। আর এদিকেও দেখুন এগুলো করতে পারবে, লার্ন মডেল কম্পোনেন্টস ফ্রম অবজারভেশনস। আর দিস আর ডিফারেন্ট চ্যালেঞ্জেস, এগুলো সব প্রবলেম যেগুলো স্টুডেন্টসরা নিতে পারে। যে আমরা সকলেই জানি একবার এলিন হচ্ছে, কখনো লার্নিং আছে, এই যে সুইচ হচ্ছে এর জন্য হোয়াট ইজ দ্য কজেস, দেন হোয়াট ইজ দ্য প্রাইমারি ড্রাইভার ফর দ্য র্যাপিড ইন্টেন্সিফিকেশন। আজকাল কিন্তু আমরা সকলেই দেখতে পাচ্ছি যে এই সাইক্লোন যখনই হচ্ছে খুব র্যাপিড ইন্টেন্সিফিকেশন হয়ে যাচ্ছে। এর কারণটা কি? এটার জন্য খুবই রিসার্চ চলছে। দেন হোয়াট ডিটারমাইন্স দ্য টাইমিং, লোকেশন অ্যান্ড ইন্টেন্সিটি অফ ডেডলিয়েস্ট টর্নেডো, এটা গত বছর আমাদের রাজ্য হয়েছিল। Then what are the mechanisms for stratosphere, troposphere coupling and eddy connections involving the stratosphere? Then accuracy, lightning forecast. Then socio-impact analysis of the weather and climate services. Then problems, এই যেগুলো কেউ জিজ্ঞেস করছিলেন যে এই সাবক্রিটিক্যাল ফিজিক্যাল প্রসেসের রিপ্রেজেন্টিং অনেক সাবক্রিটিক্যাল ফিজিক্যাল প্রসেস হয়, যেমন ধরো রেডিয়েটিভ ট্রান্সফার, কনভেকশন, ক্লাউড মাইক্রোফিজিক্স, মাউন্টেন ড্র্যাগ, এগুলোকে কিভাবে ম্যাথামেটিক্যালি এখানে করা যেতে পারে। দেন ডাইনামিক ইনস্টেবিলিটিগুলোকে কিভাবে অ্যানালাইজ করতে পারে। এগুলো দেয়ার আর মেনি প্রবলেমস আর দেয়ার। তো আমি এখানেই শেষ করছি। থ্যাংক ইউ ভেরি মাচ। এটা তো সিট হয়ে গেল। হ্যাঁ,
Thank you, sir, for your lecture. So, any more questions from the audience? We already had a few questions during the session.
হ্যাঁ, এই ফিল্ডটা টোটালি নতুন স্টুডেন্টদের কাছে, সো আই ডোন্ট এক্সপেক্ট কোশ্চেন্স ভেরি মাচ অ্যাকচুয়ালি। তো এই জন্য আমি কোনো এক্সট্রালি দ্বিধা ছিল।
We have a lot of questions.
হ্যাঁ, টাইম ইজ অলসো।
Time is always a factor.
হ্যাঁ